really one of the gurus that I get to know, and I'm also very glad that he's here today as well with us. Eric's going to take us through an end-to-end driving, full self-driving architecture, and also how it's powered by transformers. And in the end, we will also have a panel discussion, and in the panel, we will have our own chairman of Stockholm AI, Ali Leilani, who is also CEO of Eco Alpha, pioneer of next generation security solution for autonomous AI system, enabling safety and scalable deployment in critical environment. Amit Suvir, another of our experts within the field of computer vision, machine learning, over 15 years of experience, has a really deep knowledge about both autonomous as well as like the sensors, LiDAR that is using in autonomous vehicles. And lately, I think he has been also involved in developing drone vision work. And Joanna, also part of our board, she's going to actually lead the panel discussion for us. She's also an AI engineer trained from Group, working on vision language models for next generation driving system. And she is also one of our beloved board members, and you all please come and reach out to us if you want to have a discussion, if you want to know more about what we do and what we are up to. And the last slide is about the ones that hasn't been a member yet. So this is your opportunity to take a picture and become our member. Looking forward to that. So with that, I would hand it over to Hampus and take you through the presentation. Thank you.
Thank you, sir. Thank you, Reza. And I guess on behalf of both myself and Eric, thank you for inviting us here. Two simple kids from the West Coast, I was about to say. So super happy to be here. Hope the presentations and the panels and the mingle after will be interesting. So just a little bit of context, perhaps, before I get into it. I'm going to introduce the company, Zenseact, a little bit. And talk about our vision and our mission and a couple of interesting things that we do. I'm going to bring up a couple of AI use cases and reflect a little bit about like the productivity gains and the return of investment that we see in the shorter term and in the longer term. And then I'm going to hand over to Eric after like 20-30 minutes. And he's going to go much deeper into architectural perspectives of the different models that I bring up here. Anyway, good to be here. My name is Hampus Luslak, CFO and CDO of Zenseact. So it means that I'm responsible for everything finance. But perhaps a little bit more important for the talk here today, I'm responsible for all our digital initiatives, including also not just investing in, but also like delivering what I believe is one of the country's most capable deep learning infrastructure platforms. So briefly about Zenseact, we are what I believe, a little bit to Reza's point there, we're pretty big concentration of deeper AI talent in like the country perspective and from a Nordic point of view. We develop everything from like the foundational deep learning infrastructure, most parts of the data pipelines. We have for almost a decade now nurtured DL tooling ecosystem on top of that. On top of which we develop a couple of different models for different purposes here, and I'll go through this a little bit later. So I guess just understanding the essence of Zenseact, we're very much, not in all cases, but in many cases we're builders, right? In terms of infrastructure, pipelines, tooling, but also like the models. I'm not saying that because it's like right or wrong to be a builder or a rapper or whatever you want to call it, but I think that's important to understand in order to understand the essence of Zenseact, basically. We are owned by Volvo Cars. We deliver what was recently rated as the safest mobility experience on the market to Volvo and Polestar cars around the planet. So I mean, we get a lot of attention for the technology that we developed 5+ years ago. It was very much about autonomous driving, right? A lot of people was attracted to that. December 22, ChatGPT happened. After a while, people figured out that Zenseact had been on the AI train since quite a long time, and we got a lot of attention from that, basically. I mean, that's cool and all. It's super fun to be here.
Here and super fun to be out talking about what we do. But I think what we gather around constantly is that we go after like the 1.5 million lives that are saved or that are lost in traffic every year. By doing that, we also go after like 50 million plus lives or accidents that happen in traffic every year as well. I think we will relate to this a bit
differently. I mean, I relate to this. I'll take a perspective. I soon have 3 kids under or 3 or below. So I'm taking the perspective that in 15 to 18 years, the work that we're doing enables that I can send my kids out in traffic in a reality where the probability of accidents is very, very, very low in comparison to where we are today. And that is worth working really hard for. And I guess we all see and we all gather around the fact that AI and autonomy presents an enormous opportunity for traffic safety. And that's very important. We refer to this mission as towards zero faster. Zero is for zero collisions, and faster is a very important part of this message. It's very much a underscoring of that we see fast iterations in our development flow as a necessity to get there. Basically, we want the lead time between when we stream data from the fleet, retrain our neural nets, and ship better and safer software to cars around the planet to be as short as possible. So the consumer-facing product that we develop is basically a full stack capable of autonomous driving. That means that we develop every single AI and software component in this stack, meaning that we develop everything, or we train a neural net basically to create a 360-degree worldview around the car by doing that, detecting objects, classifying objects, predicting the intent of those objects, utilizing that information to understand what the environment is now and probability of what it will be in the near future. And by doing that, proposing safe trajectories for the car to take moving forward, basically. So what we refer to as, we used to call this the machine, now it's the AI factory, it's with the trend. But this is really much a foundational part in what we do, right? On a very simplified level, I think this is very much the backbone of the company. Moving like from the top left, going clockwise here, it's very much about creating the capability of streaming data from the customer fleet, automatically curate the interesting data points from that total data set, utilizing that curated data set to train our neural nets, and then when assessed better and safer, basically ship software as often as possible to the global fleet over the air. That's the essence of it. I know when I came into this industry, I was kind of like, how hard can it be? Truth be told, this is one of the hardest. I mean, we're in the business of hard problems at Zenseact. That's the only thing we do. But this is one of the hardest one to crack. Solving this process in the context of global industrialization, embedded environments, and in the context of automotive, it's really, really hard. So obviously for like any AI company, like data is an essential part of like the playbook, right? A couple of principles here. I mean, we stream a very big data set, but we don't believe in pure brute force volumes, right? So we, like many others, of course, wants to secure that we have the best possible data set. Also in our industry, we want to make sure that we can query the needles in the haystack, if you may. So what we go after in terms of scenarios is really what's interesting is really the data points that are far out in the long tails of the standard deviation curve of things that can happen in traffic, basically. In order to facilitate it, what we do is that we develop a dynamic querying system where our backend team can basically query what type of scenarios they want to source. So if you're interested in training on like elevated roads in Southeast Asia, we can query that from the fleet in that region. Same if you're interested in like bikes attached at the back of a car on Autobahn, you can query the fleet in that region to collect that data for you, utilize that for training and so on and so forth. In terms of training, I mean, Eric is going to go much deeper on this later. I can just mention a couple of things. We're progressing from like an architecture that is a little bit more modular on a very high level. I guess it's the same for all robotics, but we've had a perception layer, planning layer, and like a control layer. And for some years, like AI has been deployed in the perception layer. And I think that's kind of standardized in the industry by now, I dare to say. So what we have done now lately is that we have deployed AI end to end throughout that entire stack. And Eric will go through this from an architectural point of view soon. and for various different reasons. But that also, so that model will have to perform in a broader context, in much more complex contexts also, and it's bigger. So it needs a much bigger data set in order to leverage the performance opportunity in the model. And by that also much larger GPU cluster in order to facilitate the training of those models and with that data set basically. So I mean, we curate our training data set from like hundreds of petabytes of data. So it's a pretty big operation. And we have a couple of really, from my point of view, big proprietary GPU clusters that we train on. I also want to point out another thing is that you see the scalability or like the increase of things in the AI landscape. Now you see the investments, you see the GPU cluster. You see like players buying nuclear power plants and all sorts of stuff, right? I think 1 year ago, some of us gathered around the fact that we need to also innovate around like the data set, and we need to innovate around the GPUs in order to make this more scalable, in order to make this more efficient. And I think here, I just want to say that like over like the past 6 months, without being exactly right on the numbers, we have taken a data set that we have to train one of our models from like the size of 15 petabytes down to 1.5 petabytes without shrinking the amount of data points in the set, which is an enormous like efficiency and productivity contribution. Same here for our deep learning cluster. Depending on how we orchestrate across our DGXs or our GPUs, we can sometimes increase like 20, 30, sometimes 40% efficiency in how we utilize the compute cluster. And I think this is a massive trend for those companies that have been in very much the end-to-end sort of AI space for quite some time. And this is very important for this to sort of scale in a reasonable way, to be honest. I'll leave it there. I'm going to touch on a couple of our sort of models that we develop or the use cases, and try to connect a little bit like the productivity gain, ROI, and then I'm going to leave it to Eric to go through the architecture later. But the obvious use case is for AI here is that we train a neural net to basically automate the driving task, right? As I said before, that means that we train a model to basically create 360-degree worldview around the car, detect objects, classify objects, predict the intent of the objects, and propose like a safe trajectory for the car moving forward, right? So as you can see here in the video, the model is basically detecting dynamic objects here, cars, pedestrians, bicyclists, or whatever. Important factors to understand how to basically handle traffic. I think going into another part, cameras are great and we use them a lot. That, like, I would dare to say from a sensor point of view, like that's our backbone. We also use something that we call LiDAR. And it creates something that looks like a 3D environment almost, right? In the industry, we refer to that as a point cloud. And as you can see here in the different point clouds here surrounding the middle, you see that we can detect like the same objects in the point cloud as in the center where you see the camera screen, right? And I guess important factor, cameras are great, but they have weaknesses, right? So darkness, certain weather conditions and stuff like that. Cameras sometimes perform poorly. And this is one of those cases where it actually makes a lot of sense to have a LiDAR. Here, LiDAR is much less sensitive for like darkness and certain weather conditions and stuff. So you could detect like an object like this 100, 200 meters in advance, depending on what you work with. Connecting a little bit to like, what do we get out of this? I think in the absolute long term, it's all about towards zero. I really believe in that, and that is important. There are probably people in here that can relate to someone that actually died or experienced like a serious injury in traffic. It's important to utilize this technology to go after that. I think in the medium term, honestly, I'm very convinced looking at what we and our competitors are doing. I'm very convinced that I can send my kids out in traffic in between 15 and 18 years, and the probability of accidents are very, very low. It will happen on a rare occasion if we continue to do this. Also, we know that for every release that we make in the short term, we're lowering the probability of accidents in traffic. And I think that's, if you zoom out, that's actually an important problem to go after. A couple of other things that we do. So we utilize a neural net to automate the curation task. Basically, going back to the analogy I did before, it's very much to train a neural net to find the needles in the haystack here. What happens here is that our users go in this case, just query a pedestrian on the street, and you get like a neatly curated data set back that is very relevant for you. I think in order to understand like how that use case actually impacts us, you need to go back to like how did we used to do this before? So what we used to do here is that we would allocate like senior engineers, data scientists, or something similar, and they would plow through an enormous data set looking for like a 10-second video stream that's better than the other, right? So automating this task, first of all, great contribution to the health and well-being of those engineers. They can be reallocated to other things that are super important for us and super valuable. But I mean, 10x is probably just a slogan here for something that's growing really big, right? It's probably 20, 30, or 40, to be honest. The most important part is that we leverage AI or a neural net here in our development flow to increase the speed towards zero faster, etc. So this is pretty ninja, to be honest. We brute force train a foundation model on an enormous, like almost our total data set in an unstructured and unprepared way. So we just send like raw data on this model. And we basically train it to automate like the labeling task. For those of you who look at data labels every day, what this video shows you is that you see bounding boxes around cars, around pedestrians, and so on and so forth, that are more or less laid out as perfectly as a human labeler would have done it after having like 10 years experience. So this is a pretty spectacular, for us, it's pretty spectacular application of like Gen AI in our development flow, basically. I'm gonna put my CFO hat on a little bit and just reflect on like productivity gains here, both near term and like midterm. So we already see that we are driving the level of automation in this task quite high. Over the coming years, we will approach like 100%, and I'm pretty confident that we will drive the cost of annotation or labeling down towards like 90% of today's levels. And to be very clear here, we're coming from a level of like hundreds of millions of labeling data labeling budget annually. So I'm going to stick my neck here, my cheek here out a little bit and say that over like 4, 5, 6, 7 years, there's a possibility here that we're adding 1 billion SEK straight to our bottom line by automating this activity. And this is really like, from my point of view, taking the CFO hat on and a little bit the technical hat, an enormously beautiful case of innovation-driven cost reductions, right? Moving forward, I think always what's more than money is potentially time for us. It's really important with development speed. And these numbers are a little bit directional, but I think they underpin the point anyway. I mean, we're coming from like a lead time with labeling of somewhere between, on average, perhaps somewhere between like 6, 8, 9, 10 weeks or whatever, sometimes shorter. Basically means that we curate a data set and we ship it off to an external supplier when we get the feedback back in like 8 weeks or so. And that's how we've worked, and that's been fine. We've had great partnerships to do that. What we see now, utilizing, first of all, auto curation, and then also utilizing the foundation model, we cut this lead time down to 8 hours. That means that Eric's team can like plan an experiment on the Tuesday and run it on the Wednesday. And this is a remarkable change of how we do things. And this is also, I don't know, seeing this a little bit from the outside, to be honest, like we planned a lot of investment in this specific case like a year and a half ago. And like now seeing it actually being harvested is really, it's awesome. It's really cool, actually. So this is a little bit abstract. Eric is going to take this later as well. So I'm going to stay at quite a high level and try to make this as simple as it possibly gets. But basically what we do here, and I want to be clear here. So in the other areas, we're a bit more mature. We run things in production. This I would consider, we're very far ahead in terms of like the general market. But I still think that it's quite some time before this is in full scalable production, just to be clear and a little bit humble towards this case. What we do here is that we utilize sensor data to train a neural net to basically recreate synthetic environments that are very similar to this. So this is a camera stream from a car that you just saw. So we take that camera stream, train a neural net, and task it to recreate synthetic environments that are very similar. So I'm going to show you now a couple of use cases where the neural net has recreated like the static environment, being like the road, the buildings, the sky, whatever, and where we edit like the dynamic objects like the cars and so on. So first here, we have basically removed a lot of the dynamic objects in this scene, right? This other environment, we have created a scenario where we have a harsh brake, and the system needs to basically handle that. Bottom left, we have created a scenario where the car in front of us stops, so we need to avoid a collision basically, and at the bottom right, we have created probably the nastiest of them all, an oncoming collision here, a black car coming in. So I just want to be clear here, for those of you who didn't follow, what I showed you on the previous slide is what we normally refer to as reality, right? What I show you here, it's an AI-generated video game, more or less, based on the sensor data from our cars. And this is, from a technological point of view, it's pretty magic. Reflecting a little bit like on the scalability of this, right? So I mean, you can take just the brute force size. I mean, normally we equip like data collection cars, 30, 40, 50, we drive them around the planet, or we query from the customer fleet or whatever. This is just a neural net that could mine scenarios, right? So the range could be really big. I think even more importantly, I talked about the needle in the haystack before, or the edge case scenarios. We can generate things here, edge case scenarios at a scale here that is unprecedented if you just compare it with like what we can collect in the real world. I think even more importantly, and I think this is like more like a directional potential, is that in this environment you can create safety critical scenarios that are so dangerous that you wouldn't want to uncover them in the real world, right? And we can test and validate our production model that's going out in the real world on those different cases. And that has an enormous possibility from so many perspectives. CFO hat on a little bit again, just elaborating on the directional return of the productivity gain from this. Best case is to look at how we used to do things. So what we used to do in traditional like data collection would build like 30, 40, 50 cars. Those cars would be like 4 or 5 million a pop. We put 2 drivers in every car, send them around the world, some driving, some flying, some goes on a boat, whatever. The entire world. So they would drive for like a year, collect a lot of data that would be super interesting for us from many different perspectives. But if you just compare like the potential here, you take 1 car and 2 drivers, it'll drive for a year, collect lots of interesting data, but it would uncover on average 1 safety critical scenario during that time. That means like a scenario where the car would have to automatically intervene or have one of those oncoming collisions and so on and so forth, right? If you just take the directional comparison with the synthetic data creation here, let's say we just allocate 1 GPU server. We have a lot of GPU servers, so we could do more. And then we let that mine for 30 days. We get 10,000 safety critical scenarios when we do pretty detailed calculations on this. So I mean, what I'm saying here in my sort of business, I'm giving away my playbook for how I pitch this, by the way. What I said here to the people that are forced to invest in this, or sort of, is that I can give you at the 12th of the time, 10,000 times the output at a fraction of the cost. That's the possibility of this. And then I don't even include like the time, save time. I don't include like the safety criticality or the edge case or the performance related aspect and stuff like that. So this is really, it's beautiful and interesting technology, but it's probably one of the most sort of disruptive and like pure production productivity gains. I am going to talk, I just came from like an IT event, by the way, so I dropped a couple of slides in here on our GPU cluster. I'm not sure if you're into that stuff, but just a couple of notes on like the infrastructure here, if you're into those things. So a little bit of context, I think, also to like the Zenseact journey is that 2016, the NVIDIA CEO Jensen Huang, who now is like a celebrity type of level, handed over the first GGX server. So that's basically a box with 8 NVIDIA GPUs in that are super relevant for deep learning training, unless you're, in case you're not into that. He handed over that to the first team in the world that ran experiences on it, and that was OpenAI in the US. My friend over there was part of the first team in Europe to run trainings on the first DGX version. And that points a little bit to how early Zenseact, people at Zenseact, the core team at Zenseact actually were playing with these things, right? So that's pretty impressive. Since then, we have built 4 iterations or 4 generations of deep learning clusters. I mean, starting from like really like what was seen as something big way back then, scaling up with a pretty big multiple, and now we are about to finish like our 4th generation which I dare to say on a country level and Northern European level, whatever that is, it's a very, very capable GPU cluster that is important for us. More or less said everything here. I can just talk, it doesn't really matter how big it is, it's more about how you use it and get the most out of it. But just to get a flavor, I think there probably, or be a little bit humble, there's probably like a hyperscaler or some consortia or something around that's like bigger, but put it in comparison, it's used by like several companies, probably academia, or hundreds or thousands of users. The infrastructure that we have built is used proprietary by us, which is a huge strategic advantage for us. We started building DL clusters before like we could team up with someone that actually knew how to do it. So internally we have, right or wrong, but we've built a very strong infrastructure team focused on deep learning clusters that have built all these generations basically. And we train the models here that I referred to before, the end-to-end network, the foundation model for labeling, and the NERF network that created the synthetic environment here. If you're into like the tech stack of these things, I'm running it very quickly just in case. We have a native tooling suite, so we haven't really bought anything off the shelf here. We have very much a breed here, if you put it like that. So we do all our like frameworks and designs of the models and the experience in PyTorch, which I suppose is not that uncommon in the market right now. We run the monitoring and the feedback or MLOps in weights and biases, and we utilize a Slurm to basically maximize the utilization of the cluster, which is super important for us. I mean, we're on everything NVIDIA here. We've also tried a couple of other things here, which has been super interesting, but like, I mean, we have H100s, A100s, quite a lot of them, incoming B200s, etc., etc. I think an unsung hero, if you're into these things, is what we refer to as like the high performance storage. So it's very important for us to really load data onto the DGX service really, really fast in order to deliver on our training requirements. And we utilize what I think is a pretty big, also like from a Nordic point of view, pretty big solution here that makes this cluster a little bit more of a Ferrari than it would have been without it, if you use that analogy. On like networking side, we use everything fancy from NVIDIA, like the NVLink Fabric, InfiniBands. We have also native, like a nurtured and native Ethernet backbone that we utilize for multi-DGX or multi-node training. That's becoming a super big thing for us, of course, that we have nurtured over almost 10 years now. That delivers like, I don't know, 50% the speed at 30% of the cost in comparison to leading alternative. I think this becomes more of like a country level strategic aspect on like the power and the cooling side. We're running things in terms of, the US have started talking about gigawatts now, by the way, but we still talk about megawatts. But we have a pretty big cluster, of course. We're in the low to mid single digits megawatts. But if you're going to facilitate like our build out, it's becoming it's not trivial for us to find the right infrastructure partner to actually facilitate that growth from a pure power supply perspective. So it's like almost a national thing. So if someone from some sort of government body related to infrastructure for AI, connect with me later. From the supply here also, if you're into that, I mean, we're fully air cooled right now, but we're on a stepping stone into more liquid cooling and mixing with air and stuff like that, which is super important for us also to scale up. That was that for me. Just want to say it's super fun to work at Zenseact. We do a lot of cool things, of course, and super happy to be part of so many trends blended together in a great team. Not lying, what we're truly relentless about and what we revisit day after day after day is the ambition to go after zero. And that's really what Zenseact is about, I think. Eric, thank you very much, by the way. Good luck.
I'll just do this one. No. Yes, hi, I'm Eric. It's very nice to listen to you, because usually I just fight with 1,000 different problems every day and zoom out and hear you talk about what you do from that angle is actually quite inspiring. So thanks for that. I have a background as a physicist, but that was quite many years ago. And oh, you want that?
Don't mind me.
No. And then I actually spent quite some time working with these kind of numbers, like how many people are killed and injured in traffic at Autonomy research outside of Gothenburg. And that I'm very passionate about traffic safety. I think it's an absolute tragedy every time someone is hurt in traffic. And I have also lost a brother in a traffic accident. So this really matters to me. So starting with in the automotive industry was more about being passionate about traffic safety. And then in 2013, I think it was, Google started to talk about self-driving cars. And my tech heart started to come alive. And then a few years later, I was leading a research group at Autonomy Research, and deep learning was, I came across deep learning and I was just amazed. That was 2014, 2015. So I immediately just read every paper you could come across about deep learning. There was no deep learning books back then, even. So but it was fun to get to know the technology. And a few years later, I could title myself a deep learning expert. And I try to stay updated on the latest and greatest. But these days, it's hard, right? There's 1,000 papers coming out every day, and the success with LLMs and so on. But it's an amazing field to be active in. I've had different roles at Zenseact, but I've been part of building the deep learning stuff. I was buying that first DGX machine. That was actually at Autoliv Research, and now we have many. And we have a big team. Yeah, I will talk about end-to-end driving with safety guardrails today. But we start with what is the system that we're working on together with Volvo Cars. We call it One Pilot. One Pilot is a system that, of course, has a car in which you have 1 or 2 computers powered by NVIDIA SOCs. It has a connection to a cloud where we have maps around describing the world. And on the car, we have sensors. We have a bunch of sensors around, so we can see around the car, cameras, I mean. A bunch of radars and a LiDAR. And then not all cars have both computers and not all cars have all sensors. So we need to handle a few variants as well. And then software architecture is of the essence. So this is anyway the computers, the sensors that we have at our disposal. Oh, I forgot a slide. I wanted to say that when we work with this, we think of the car as a robot. But the robot has 3 modes. You can actually drive it yourself. And then we say that One Pilot is in drive mode. So you as a driver is actually driving. But our technology is always running in the background, and it can warn you if a crash is about to happen. It can autonomously brake the car if needed. It can inform you about the traffic speeds that you are supposed to hold, etc., etc. So we try in various ways to support the driver. Then the driver can put the car in cruise mode. Then the car will drive for you. It stays in lane, it can change lanes, and it will adapt the speed to traffic around you. But the driver is ultimately responsible for supervising what's happening and takes a lot of the safety responsibility. And the holy grail is then to do ride mode, where you as a driver becomes a passenger and you're just riding. We have not yet released Ride to customers, but it will come, and it is built on the same architecture. It's the same software in Drive, Cruise, and Ride. But of course in Ride we need it to be more or less perfect, and a lot of redundancies all over the place. So our first generation of One Pilot was released a while back. It runs in Polestar 3 and EX90s. And we were among the first to really build a computer vision stack from the ground. We started from scratch a while back, and it's relying mainly on deep learning. So we do these object detections, free space and road edge detection, and also this function that we call holistic path, where the neural network looks at an image and tries to estimate where should you drive the car. And we're super proud about this. We spent a lot of time and effort doing this. We annotated millions of images to train these neural networks to become robust against everything that can happen in traffic. And as Hampus mentioned, we have also the highest rating in Euro NCAP ever when it comes to active safety. So we're super proud. Having said that, there are limitations with this technique. The neural network looks at one image at a time from one camera. So if you want to say where to drive, you can outline a path, but you have no idea. The network has no idea about how fast is things happening because it only sees one image. So it cannot say how fast to drive. It cannot output a trajectory. And this talk is about end-to-end driving. If you want to do end-to-end driving in a network, you need to also understand velocities. So a sequence of images, hence a video, is needed. So the first generation of deep learning, you have sensors, you do detection. The detection box is green. This means here we use deep learning. But then we do fusion of all the different sensors and tracking using extended Kalman filters. Prediction is also done with classical methods, planning and control. It's all classical, which I chose to color red here. What we are now working on is to do an end-to-end sensor fusion and trajectory planning in one single neural network. So all the sensors, if you're sitting at the back, you might not see it, but all the sensors come in, and then this one big neural network fuses the information from all sensors. It does detection, fusion, predictions, and trajectory planning in one go. So this is, of course, an extremely much more complicated architecture. But we think we can do it, and now we have proof points. You will soon see some what we have in development. What is enabling all this is that we are going from a computer with 30 tera operations, NVIDIA Xavier, to an Orin X, which has 250 tera operations, so much more compute. That is a necessity to do such a thing. And it will lead to improved customer functions, faster development speed, and we can work completely data-driven. So we call this DL2, Deep Learning 2, our second generation of deep learning. And if you zoom out on this network, basically there is a bunch of sensors coming into a big neural network. It outputs objects, lanes, free space, road edges, etc. I just outlined that on one arrow. Those things that are human interpretable, things about the world state, we train the network by showing it annotated, labeled data. So supervised learning on data annotated. And going from just one sensor to all these many sensors and to sequences, the cost of annotating manually just explodes. I mean, hundreds of millions would not be enough. It would have been billions each year, and it would just not be feasible. So Hampus and I and a few others, we spent a lot of time talking and thinking about what to do about this. And the result was that we have to train what we call a foundation model to support with the annotations. So I'll talk a little bit more about that. The other one then, the end-to-end part here, the network also outputs ego trajectory proposals. Where should the car actually drive and how? And here we use something called imitation learning. So we just show the network a lot of videos where humans have driven as one should drive, and the network is trained to imitate that. This is very similar to how you pre-train a large language model. Because what is it that you do? The large language model sees a few words in a sentence, and it's supposed to predict the next word. That's just imitating how humans write. That's fairly easy to do because that is a categorical space of words, whereas here you have a continuous action space. So it's much more unstable to do imitation learning for driving a car compared to predicting the next word. So you need to have a lot of tricks in your learning curriculum to make it work well. But it's still a super powerful technology. And then what we are also trying out is to post-train this ego trajectory proposals
with reinforcement learning. And then you need a simulator. Enters those neural simulations that Hampus talked about. So that is the ultimate goal, to use neural networks as a simulator to train another neural network to drive the car. And we're working very hard on that. And this is also similar to what you do with LLMs, where you have this reinforcement learning with human feedback as a post-training step. So all we do here is very inspired by LLMs. Zooming in a bit more, I said I was going to be generous with architecture today. So if you look at the architecture of this neural network, it has a lot of transformers in it. And transformers is the architectural block of LLMs, right? They do attention. And there is this famous paper from Vasvani et al. From 2017, attention is all you need. That also goes for self-driving cars these days. So basically what we do, we have these sensors, a lot of cameras, a few radars and a LiDAR. We encode them one by one, typically using a CNN, a convolutional neural network. The output of the CNN is a feature map. And then the feature maps from all these sensors are fused with a transformer that does spatial cross-attention. And this is a really tricky operation, because this sensor fusion block in the middle needs to also understand in which direction is each sensor looking. So you need to do, in LLMs, you positional encode words. We position encode the calibrations of sensors instead. And since it's temporal, we also need to do temporal encoding of the time at which the sensor measurement was done. And not all sensors run synchronously here, rather the opposite. They're more or less all asynchronous, and they run at different frame rates. So just to design this system and enable it to make sense of all the data is actually quite a challenging task. And then this transformer network in the middle that I talked about that does cross-attention to all the sensors, it's also temporal, which adds, it's a recurrent neural network, right? So that adds complexity to the training as well. The output from this transformer in the middle is some kind of neural representation of the state of the world around the car. We as humans cannot understand this, but it's a very rich representation, at least if we train it well on good data. So now we want to decode that into things that the driving stack wants. So we can have, we actually do have an object head, which is decoding those world vectors into objects. And we output 3D bounding boxes. Those are human interpretable, and the planning teams at Zenseact can write code for safe trajectories and nominal trajectories. And the same goes for lane lines, road edges, parking spots, etc. Those heads are also transformers, by the way, and they're also recurrents. So you see we have a lot, you see those arrows which are a bit curved here, they're indicating recurrency. And we're training all these tasks at the same time with all these different recurrencies, with all these different sensors. It is a bit of a beast to train, actually. And then comes the most exciting one then, the ego trajectories. And I draw it a bit to the right under the planning box here, because it's actually doing planning right. Based on the world vectors, this head is planning how the car should drive. Now you can turn your attention to the safety guardrails, the brown box to the right. So the brown box, it has more classical trajectory planning based on the objects, lane lines, road edges, and free space that it gets, and it outputs how the car should drive. And then we compare that trajectory to the one proposed by the network, and we have a mechanism to select the best candidate. It's not trivial to do this, and we're still experimenting how to do it best. And at the end of the day, we get a safe trajectory that the car can follow. And this is where end-to-end trajectories comes from. That there are pixels and radar measurements in, and the network outputs a trajectory that the car can follow. Hence end-to-end trajectories or end-to-end driving. So this is complex, right? But it's still a simplification. So I said that not all cars have all sensors and not all cars have all computers. So we need to also, we don't like variants much. I used to work as a chief architect at Zenseact, and my motto and slogan was fight variants. So how can you do that? If you think carefully, you can actually have a pretty clever architecture. So what we do is that some sensors are routed to one computer, and we call it cluster A. And other sensors are routed to the other computer, and we call it cluster B. And now if you buy a little bit cheaper car, you only get the cluster A. And if you buy the more expensive car, you get both clusters. So then we have, you can see in blue, it's more or less a copy of the network that I just showed you here, but it's only consuming the cluster A sensors. And then we did a similar copy on cluster B that we can use as a fallback solution if something would happen to the computer on cluster A or to the sensor on cluster A. But we also wanted to give the guy or girl who buys this expensive car the ultimate ride, right? You want to be able to extract information from all sensors. So we introduced cluster AB, where we fuse the world vectors from both cluster A and B. So you can think of it as there are actually 3 drivers of this car: cluster A, cluster B, and cluster AB. And if all is nominal and jolly good, cluster AB does the driving. If you bought a little bit cheaper car, cluster A always does the driving. And if something goes wrong and it's in ride mode, cluster B would take over driving. So you get redundancy. And now you can choose to deploy all these clusters on the same computer or on various computers depending on how our customers decide to route the sensors. So it's a very flexible yet quite elegant architecture, but it is also complex because then we train this neural network in one go, everything together. There is one more little, actually quite beautiful thing about this construct, and that is that in the old days, in DL1, we annotated boxes and lane lines in each image. So each sensor would be annotated individually. Whereas here we do all annotations in 3D. So if you annotate one object in a sequence, it gets automatically annotated for each sensor or each cluster as you wish. And this enables us to train all clusters simultaneously without adding any annotations. So we did a lot of thinking, and we did a lot of convincing that this is the way to go, rather than squeeze out all the juice you can from DL1. We motivated, like our company and our friends at Volvo Cars, that this is the way to go. It's an opportunity or a risk, depending on how you see it. And we are in the middle of this transformation as we speak. My phone is buzzing because the teams are out driving with the newest network that was deployed yesterday. It's not in production yet, but we're building this thing, and you will see a little bit what it looks like. So the end-to-end trajectories. This is from yesterday's model as we run it in resim on a lot of data. So this video takes a bit of explanation, so I'll talk you through it. In the bottom right, you see a visualization from the front camera, what the world looks like. And then the green line, this is the best proposal from the end-to-end network. And in blue, on the same picture, it's the ground truth. This is how the driver actually drove the car when collecting the data. The thing is that sometimes it's more or less, or it is impossible for the network to know in advance whether the driver took the right or left turn in an intersection. So if you only give the network one guess, it is prone to guess in between left and right, and it will run into barriers. So we equip it with 6 proposals. This enables the network to guess right, left, straight ahead, change lanes, etc. So in the visualization to the left, we look at the same scene from above. In blue, you see how the car actually drove, and in red, you see the different proposals from the network. And we want at least one of the proposals to coincide closely with the ground truth as what the driver actually did. But sometimes in an intersection or so, It's okay to have some proposal taking a right turn and another one taking a left turn. So this is why you see those red lines curve out. And the length here, of course, corresponds to the velocity. The faster you drive, the further you get. And the horizon here is, I think, 5 seconds. So it's looking promising, I would say. Then the tricky part is to close the loop in a car and actually drive on this thing and get that to be stable. And this is what the team is out doing now as we speak. Yeah, and just for completeness, the plot to the top right is showing elevation, because we want the network to understand if we're going uphill, downhill as well. Those were the trajectories. That will be the future. But we still want to understand what the world looks like with objects and lane lines. One reason for that is that we can build safety guardrails, and we can choose another trajectory than the end-to-end one if we think it's safer. So here is the network, the same network then, but the output from the object head. Again, in the top view, you see the front camera, and you see the different vehicles that it detects in green. It's not matching perfectly because this network is predicting in 3D at a certain frame rate, whereas the camera might run at a slightly different frame rate. There is calibration issues, a lot of things. So it's not even designed to project the boxes perfectly back into the image. But it's still looking quite good, right? It's detecting more or less all objects and not so many other. And then all the green boxes you see in all the other views, it's the same boxes, it's the same objects. It's just that we project them into the different sensors to visualize what it looks like. So if I move here, this is the point cloud from the LiDAR, and then the objects that the network detects is projected on top of it. And the reason it can detect boxes behind the LiDAR is, of course, that we have cameras and radars looking behind us. So the two black panes in the middle is the front-looking radar and the corner radars. And then you have fisheye cameras and rear-looking cameras here. This network has not seen one single manual annotation. It is completely based on automated labeling from the stuff that Hampus talked about. And I wanted to talk a little bit more about that. It has also still not seen super many sequences. So if I was here just a week later, it would have been trained on twice as much data. And then it would have looked maybe not twice as good, but significantly better. So we are at the point in time where we have the architecture in place, everything is connected, and we're just feeding it with more and more data and trying to squeeze out as much we can from the GPU cluster. So to select sequences is a hairy problem. And you talked about this, Hampus, that we utilize AI models in order to search for a varied training data set. Variation is key. Diversity is much more important than quantity when it comes to training these models. And I think LLM companies are starting to realize the same thing. They spend less and less time scraping the internet for more and more time to get rid of bad data and have diversity in their data sets. It is easy to be jealous about the money that some companies spend on AI, but I know that you can be very competitive by being clever instead of throwing very much money on the problem. Then if you're clever and throw a lot of money, that's of course hard to beat. So this neural network that is annotating the objects around us that the DL2 network was trained on. The first thing we do is that, the current generation of this, we call it the foundation model. So let's call that the foundation model. It's a transformer network that is operating only on ground truth LiDAR. And we pre-train it on basically all data we have ever collected without any curation. And we train it to predict how the LiDAR point cloud will evolve over time. So we show it a sequence of LiDAR scans and we ask it to predict what will it look like in the future. And then we also have a way to infer Dino features. Dino is one of those foundation models from Meta that can do semantic segmentation, and it knows about basically all the things in the world. So this network is learning neural semantic classes in the pre-training as well. So based on a point cloud, it can predict how the world will evolve and what is in the world. And if you can do that, you basically understand the world. So pre-training like this is just a massively powerful technique. And we wrote a paper about that. We call it GASP, which has been submitted for publication. And it's just a game changer. So having this pre-training, that takes, I mean, we have one training now. It's been training for 2 months, I think. So that we can just train and train and train. It gets better and better and better. Then we can show it quite few manual annotations, and it learns the task super quickly. And then we run it on our well-curated training data set, and it does this labeling for us. And I chose to show you something from a highway, a rainy city, a crowded city with a lot of pedestrians. You would not believe, or maybe you can, because I guess many of you drive cars or walk around in the city. I mean, the amount of strange scenarios that can happen is just really, really big, right? And this network handles, I have actually not seen a major miss from it yet. It might have a false positive sometimes and a false negative, but that's not really a problem. And the accuracy it's just amazing. Yeah, we have another way to do automated labeling as well, where we actually apply good old-fashioned computer vision. So this is a point cloud reconstructed just from fisheye cameras. So we drove around this parking lot, and I think maybe you saw it already, the poses of the car. So we reconstruct how the car drives, then we can do structure from motion, get this point cloud, put the images colors on the point cloud, and then in one shot annotate all the parking lots or parking spots. Oh, actually it's parking slots in a parking lot. Whereas a parking spot is a parking slot without the lane markings around it, I've learned from the team. Yeah, so this is an automatically labeled parking lot. And then we can use this and train the DL2 network to also predict parking slots. Yeah, so that was automated labeling. Then finally, a few more words on this neural sensor simulation. So I find it very, very stimulating and fun to go to these AI conferences, CVPR and ICCV and ECCV. Those are my favorites. And since few years back, there was a paper about nerves. And it's like, what is this? Neural radiance fields. Pretty cool. Next time I went, half of the conference was about nerves. It's like 2,000 papers at least. But what happened? And then next year, nobody wrote about nerves. It was all about 3D Gaussian splats. And now people talk about 3D Gaussian ray tracing. What is that? Maybe you're into it, but if you're not, it's like you said, Hampus, you're using machine learning. You feed a neural network or a set of Gaussians images, and this machine learning algorithm learns what the scene looks like. And you can query it from images from novel views. So this basically can serve as a simulator for us. And this is already proving useful for us. But the hope is it will be the real game changer where we can then fine-tune our DL2 network. And this looks very promising, I think, when you look at it this way. It's just that for it to be really, really useful for us, okay, I should go back. We don't want just the front camera, right? We want all the cameras and the radars and the LiDAR. And the technology is getting there, but it's not really ready to do all we want to do with it. But we are quite invested in this. We have at least, I think we have eight PhD students working just on this. And they are publishing in the best journals. And we are also working with a supplier on this, Parallel Domain. And we have some in-house activities. So we are very invested in this space. And we think it will be the next big thing. And then we'll scale it up. And then, yeah, we'll see. That concludes my presentation. And if you're interested in Zenseact and want to know more about us, please reach out to me in the Mingle section. Thank you.
Great presentation. Thank you very much, Hampus and Eric. You were amazing. I mean, I'm so impressed, guys. I mean, I had the opportunity to work with the Zenseact team, I think like 3 years ago or something like that. The progress that you have done, wow, amazing. So I think we will probably take 5 minutes break before we start the next session, which is your questions and the panel discussion.
Thanks.
Va? Det där var ju grymt. Shit.
Tack.
Jag blir såhär nördrysningar.
Det är riktigt nördigt alltså, det är häftigt.
Jag gillar det, men det här är precis vad vi vill. Det är precis sån här prestation som vi vill ha här. Vi har det tror jag. Jo men det kommer komma frågor från... Ja, men det kan jag.